Yeah, so students, so please confirm me. Am I audible to you? Can you all see the screen clearly? So good evening students, welcome back. So please type in the chat box, am I audible to you? Can you all see the screen clearly? I think chat box is not right. Just a minute. So please type in the chat box, am I audible to you guys? Can you hear me? Good evening 𝐂𝐚𝐿. So please confirm the audio once. Am I audible? Yes, audible. Okay, fine then. Okay, great. So let's continue. So this is going to the first lecture of this new module, control volume analysis of fluid systems. Okay, so this is control volume analysis of fluid systems actually. So we will try to understand how we analyze the control volume. So because sometimes what happens whenever, like in previous case of differential flow, we know whenever there is some flow is happening, we will pick some small differential element and we will try to study what's happening. But sometimes it's not possible to pick the small element. Whether instead of picking that small element, you have to take the complete volume or the complete element that's available into consideration to understand something. Means let us suppose, for example, let us suppose if for example, let us suppose if there is a rocket. Okay, then what happens when combustion happens? Because of the velocity of the exhaust gases, the rocket moves in the forward direction. Now to understand this motion, you have to take the complete rocket into the picture, correct? Because the complete rocket is moving. It's not like you take some small part within the rocket and you start some analysis. This don't happen. Okay, so sometimes differential analysis cannot give you good solutions. Okay, so that's why control volume analysis of systems is sometimes very important to calculate the effect of fluids on that particular systems. Okay, so we will start with that. So let us see the quick review what we are going to discuss. We will solve the numericals which were left over in the previous lecture. Some 5-6 questions were there. Then we'll provide some good introduction to the control volume analysis, and also we will see the mass conservation equation. Of course, you have seen the mass conservation equation in differential form. Now in this session, I'll show you integrally how we can actually come to the mass conservation equation. Okay, so tomorrow we will go to one very important thing which is called the Reynolds transport theorem actually. Okay, so before that we will have some quick introduction today, what we are going to discuss in a detailed way. Okay, so now first thing, let us finish. So if you revise, so we have talked about previously in lectures, like we have talked about the free and forced vertex flows. Free and forced vertex flows is what we have studied about. Okay, so we have seen in this case these are irrotational flows. Irrotational flows. And here we know these forced vertexes are basically rotational flows. So we have seen certain things, like in this case the velocity variation. If you see, the velocity variation in this case is inversely proportional to r, and p is proportional to -1 by r square is what we have seen. And similarly here we have seen v theta is equal to r omega, which means v theta is proportional to r and p is also proportional to the r square we have seen. Okay, and main important discrimination is applying the Bernoulli's equation. So if the flow is irrotational, you can apply Bernoulli's equation at any 2 points in the flow. If the flow is rotational, then definitely you can apply Bernoulli's equation at 2 points on the same streamline. Okay, so this we have understood. So let us continue solving the problems actually. So let us see. An incompressible fluid passed an impermeable flat plate as shown in the figure. So if you see, there is some figure which is shown here. So if you see, there is one flat plate here. There is one flat plate like this. Okay, so there is one flat plate. Then what's happening to this flat plate means basically above this flat plate there is some fluid which is coming in. Okay, so this plate is impermeable. What is the meaning of this word impermeable? It won't allow any fluid to pass through this plate. Okay, so this is a fixed plate. Now let us see here. Flat plate as shown in the figure with a uniform inlet velocity profile u is equal to u0. Okay, so means basically at the inlet, if you see, let us suppose if this is the inlet section, if this is the inlet, then the fluid is coming with some uniform velocity at the inlet. Now what happens, obviously whenever the fluid enters this region, slowly the fluid layers will actually slow down because of the friction between the plate and the fluid, which is nothing but viscosity. Okay, but anyhow, right now if you see, they have given you and a cubic polynomial exit profile. So at the exit, you see, at the exit at this section, the velocity profile is cubic. Means basically if you see the velocity variation of these points, obviously as the distance moves away from the plate, the velocity of the fluid layers increase. So we know that in this case the velocity at the exit is basically cubic in profile. Okay, now where eta is y by delta. There is some expression for delta. Okay, so delta is basically this height because it's given this is the line, y is equal to delta. So there is some height delta. Okay, now let us see what happens. The volume flow Q across the top surface of the control volume means basically if you see in this case, if this is the surface which is available, they are asking you what is the mass flow rate through this surface, which is this surface. Okay, so now let us name this surface. For example, if this is A, B, C and D, for example, then definitely this is steady flow, means basically whatever the fluid is coming, the same fluid should actually go out. Okay, there is no storage for some fluid to stay on this plate. Okay, so then what happens? Look here, m dot in should be equal to m dot out, correct? Because whatever is coming, that should go out, because there is no provision for the fluid to stop in this case. So this implies, now if you see the fluid is entering through this face AD, it cannot enter through this AB because this plate is impermeable, means this plate do not have any pores, means basically this no fluid can enter this plate. Okay, it's an impermeable plate. So whatever the mass flow that actually comes through this face AD, it has two options to leave. One along this face BC, another along this face which is CD. Okay, so means whatever is the mass flow that's coming, m dot AD is equal to mass that's going out is through two faces, m dot BC plus m dot CD. Now they are asking you what is m dot CD, correct? How you will do that? M dot CD is equal to m dot AD minus m dot BC. Now let us try to calculate the mass flow rates. Okay, so here they want discharges. Okay, so obviously if you cancel density in each term, discharge to CD is equal to discharge to AD minus discharge to BC. Now how we calculate the discharge to AD? Look, this is the section. Now here if this is the section, at every point you have the same velocity, correct? At every point you have the same velocity. So whenever you have the same velocity, if you take some side view of this, for example, so if you see, for example, if you take some side view of this, you will actually have some rectangle, correct? Yes or no? This is basically some so this is how it actually appears to you. Okay, so this is how it actually appears to you. Now if this is the case, the width of the plate, let us suppose if this is width of the plate W and this height is dy, for example, and fluid is entering this, basically if this is the side view of what you are seeing. So here if you see, this is dy. Okay, now if you want, let us suppose the velocity of flow through this section is u, then this discharge to QAD can be written as 0 to delta u into width of the plate is, what is the width of the plate? Did they give you something? Flat plate as shown in the figure, width with a uniform inlet profile and a cubic polynomial u. The volume flow rate Q across the top surface of the control volume is dash. Okay, so I think B is the width of the plate. Okay, so width of the plate is B. Width of the plate is B. Width of the plate is B. Then for this small velocity, the area that is available for the flow is dy into this W, correct? So dy into W is the flow area that is available. Means if you take some small elemental strip of thickness dy, means let us suppose if this strip thickness is dy, if this strip thickness is dy, then the volume of fluid that enters this surface is dy into width, which is nothing but this area multiplied with velocity, correct? Minus integral 0 to delta to BC. So to BC also you have, if you take the small value, small section dy, so the flow area that's available is B into dy is the flow area and the velocity here at this place. Okay, so the velocity which is flowing, which is present at this section u. Now if you simplify this, now this is at the inlet. Okay, so this is at the inlet AD, so velocity profile at AD, and this is velocity profile at BC. So now let us see here, what is velocity profile at AD? This is a constant, means if you take at any value of y, this u naught is a constant. So here this uad is given by some constant value. So integral 0 to delta u naught into b, u naught into w into dy. Okay, that w is nothing but width b, which is given here. So let us see, this is b. So u naught into b into dy minus integral 0 to delta. What is the velocity profile here? You can see u naught by 2 times of u naught by 2 times of u naught by 2 times of t eta minus eta cube. So t eta, so what is eta? Y by delta minus eta cube, which is y by delta whole cube. Okay, so this is what you have multiplied with b into dy. So this is the total expression for the calculation of the volume flow rate or the discharge basically. Okay, so whenever there is certain change in the velocity profile, I told you, you take the small elemental area, then calculate the discharge to the small elemental area and integrate it from 0 to the maximum limit. Okay, so the same thing I have done. To this small elemental area, I have calculated the discharge and I have integrated from 0 to delta. Here also same thing. So the velocity profiles are given. Okay, of course in this case it's constant. U is equal to u naught is the constant throughout. So we have done this. Okay, now if you take u naught into b out from these expressions, this implies, or this is equal to QCD, volume flow rate to QCD, which is basically this, is equal to u naught into b is common. So u naught into b is common. First integration, if you take u naught into b out, integral 0 to delta dy, that if you simplify you have only delta minus second integration, u naught b, if you take out 1 by 2 times of okay. Now integration of 3y by delta, this is 3 by delta into y square by 2 minus y by delta whole cube, which is y power 4 by 4 delta cube within the limits 0 to delta. Okay, so this is the total expression. So if you simplify this, then u naught b delta minus, now if you replace delta here, this is 3 by 2 times of delta minus delta by 4 into half, correct? So half times of 3 by 2 delta minus 3 by 2 times of delta minus delta by 4. This is what you have. Okay, now if you simplify the things, this is 3 by 4, means if you multiply, okay, first of all if you simplify this, this can be written as 6 delta by 4 minus delta by 4, so total 5 delta by 4, 5 delta by 4 into 1 by 2, so total 5 delta by 8. Okay, so delta minus 5 delta by 8, so u naught b times of delta minus 5 delta by 8 is what you have. So if you simplify, 3 times of 3 by 8 times of u naught b delta is the discharge that actually flows to the phase BC, phase CD, which is actually given here. Okay, so the discharge to the phase CD is basically, you have to do this integration little carefully. So if you do, we got 3 by 8 times of u naught b delta. So let us check for this 3 by 8. So in both these options, but square is not there, right? So this is 3 by 8 times of u naught b delta. Clear? So this is basically the correct answer. Okay, so if you simplify, delta minus, so here if you see 3 by 2 delta minus delta by 4, so 3 by 2 minus, calculation is correct, right? So please confirm me the calculation is correct. 6 by 4 minus 1 by 4, so total 5 by 4 into 1 by 2, 5 by 8, so 1 minus 5 by 8 is 3 by 8, correct? I think this is correct answer. So 3 by 8 times of u naught b delta is the correct answer. So maybe some typing might have happened here, so b could be the correct answer. Okay, so DTP might have taken a wrong key, but this is the correct answer. 3 by 8 times of u naught times b delta is the correct answer, and this is how we get the correct answer. Clear? Okay, simple integration, you have to do little carefully, that's it. Did you all get 3 by 8? Okay, if you do the integration, you should get 3 by 8 actually. Okay, so let's go for the next question. The axial velocity profile in a pipe of radius R is given by the equation u is equal to um into 1 minus small r by R whole power n. What is this n? Where um is the maximum velocity at radius r is equal to R. Okay, so at radius r is equal to R. Okay, so obviously maximum velocity will be coming at small r is equal to capital R. Okay, so now then that is 1, right? So this is where um is the maximum velocity at r is equal to r. This is a pipe, correct? So means r is measured from the center, correct? So means r is measured from the edge actually. So radius is measured from the edge. Okay, right? Because you see um is the maximum velocity at small r is equal to capital R. For n is equal to 1. Sorry, for n is equal to 1 by 5, if the value of average velocity of the flow is given by u average is equal to k times of the value of k is dash. Okay, so here if you see, this is 1 minus small r by capital R whole power n. Is maximum at small r is equal to capital R. Okay, so is the maximum velocity. So maximum velocity, normally in a pipe flow, maximum velocity comes at center line. Okay, so that center line is taken as small r is equal to capital R actually here. Okay, fine. So let us try to evaluate the expression. Let us take a pipeline. Okay, so let us take the pipeline. So let us suppose if this is the pipeline here. Now in that case, this is a pipe in which there is some flow that's taking place. Okay, so there is some flow which is actually taking place. Now let us take the projections of this, for example. So if you take the projections, then so this is the pipe side view. Okay, so basically this is the cross section. So whenever there is some velocity profile, take some small elemental area through which the flow is happening. So let us take some small elemental area through which the flow actually takes place. So let us suppose if this is the flow area which you are talking about. So this is the small flow area. Okay, now this small elemental area dA, this dA is 2 pi smaller dr. Okay, so this is 2 pi smaller dr actually. So dA is equal to 2 pi smaller dr. Let us do one thing, guys. Is the maximum velocity at r is equal to capital R, but I think this is r is equal to 0. Okay, I think they might have mistyped it, but normally, because you see, whenever you are taking the radius, what happens? Radius is always measured from the center of the pipe, correct? So this is radius. Maximum velocity will be at this location when small r is equal to 0. Okay, so if you see, maximum velocity u max is at this location, because because of friction and all, what happens generally, this u maximum comes at r is equal to 0, correct? Because if you see, if you put small r is equal to 0, only then this u is equal to okay, maximum velocity. Okay, now let us see, through that small section, they are asking you what? They are asking you average velocity. Okay, so if you want average velocity, look, discharge can be written in two ways. What are they? R is equal to 0 to capital R, u into 2 pi r dr. This is one way. And if you want the concept of average velocity, you can write this as u average into pi r square, correct? I told you the definition of average velocity. What is the definition of average velocity? If you assume there is some uniform velocity all over the cross section, then the value of that velocity for which the discharge remains same through that area, means basically whenever there is certain velocity profile, look, try to understand what is the meaning of that. Whenever you have certain velocity profile, for example, normally in case of pipes, it is parabolic, which you generally see in next chapter. So if you see, normally this is the case. Now for this given velocity profile, what happens actually, you have some discharge. Now if you want the concept of average velocity is that magnitude, average velocity at this section is that magnitude of the velocity at which, if this is the magnitude that you have taken. Okay, so for example, see here carefully, if this is the magnitude that you have taken in this case, so see here, if you see at this section, the velocity is uniform at all the points, but the discharge should be same. Okay, so the discharge should be same actually for the same velocity. So then this magnitude of velocity which you have taken here in this case, so this is called u average. Okay, so this is u average velocity. Clear? So for the same area available, the discharge should be same provided the velocity is uniform at every point in the section. So that velocity is called the average velocity. Okay, now if you do this integration, let us see what comes out. So this implies integral small r is equal to 0 to capital R. What is the velocity profile? Um into 1 minus r power um into 1 minus small r by capital R power 1 by n, 1 by 5, something is given. What is the value of n? 1 by 5. Okay, so this is 1 by 5 multiplied with 2 pi r dr. So this is actually the discharge that's happening. So this discharge should be equal to u average into pi r square. Okay, so let us see first of all what comes out. This implies discharge is equal to um into 2 pi is constant, so into integral r is equal to 0 to capital R 1 minus small r by capital R whole power 1 by 5 small r by capital R whole power 1 by 5 into small r dr. Okay, now if you want to calculate this integration, it's not directly you can evaluate, you need to do a substitution. So let 1 minus small r by capital R is equal to t, because straight away expanding this 1 minus r by 5 capital R whole power 1 by 5 is not very easy. Okay, so that's why we have just taken one substitution, that 1 minus small r by capital R is equal to t. So this implies minus dr is equal to r times of dt. Okay, so this we can replace. Then what is the limits? Lower limit, if you see r is equal to 0, this implies t is equal to 1. Upper limit r is equal to capital R, so this implies t is equal to, means if you substitute in this expression we will get t is equal to 0. So let us replace all these things in this expression. And one more thing, small r is equal to 1 capital R times of 1 minus t. This is what you have. Okay, now let us substitute all these four things in this integration. So this gives you q is equal to um into 2 pi, these are constants. Now if you substitute in that integration, integral for lower limit we have 1, this is 0, this is t power 1 by 5 into small r is capital R times of 1 minus t into capital R times of 1 minus t into dr value is minus capital R dt. Now using this minus sign, let us swap these two limits. So using this minus sign, let us swap these two limits. So if you delete this minus sign here, then this can be changed to 0 to 1. So 0 to 1, 1 minus t into r dt. So this implies q is equal to um into 2 pi capital R and capital R. If you take them out, 2 pi r square times of, now integration, t power 1 by 5 into 1 minus t. So this can be written as t power 1 by 5 minus t power 6 by 5, actually correct, 1 by 5 plus 1 which is 6 by 5. So what is integration of t power 1 by 5? T power 6 by 5 and this is 5 by 6, correct, basically 1 by 5 plus 1, so that turns out to be 5 by 6 minus here t power 6 by 5. So what is 6 by 5 integration? 5 by 11 times of t power 11 by 5 is what you have. Okay, with the limits 0 to 1. So this is the discharge. So if you simplify this, um into 2 pi r square times of 5 by 6 minus 5 by 11. So if you take one 5 out, we have 11 minus 6, 5 by 66. So this is the expression which is left for you. So this is the total discharge that actually takes place. Okay, so this can be written as u average into pi r square, correct, because you see the same discharge can be written as u average into pi r square. So if you simplify the things, we have pi r square and pi r square gets simplified, then 2 cancels this 33 times, so 25 by 33. So if you see, u average is equal to um times of 25 by 33 is what it is left over. Okay, and here if you see, they have given you same thing, u average is equal to some constant times of um. Okay, so u average is equal to some constant times 25 by 33 times um. They are asking you what is the value of the constant k, round off to 2 decimal places. So calculate the value 25 by 33, you will get the correct answer 25 by 33, 0.7575. So k is equal to 0.7575, right? We got 757, 0.7575. This is the correct answer actually here. Okay, so this is 0.7575 is the correct answer. So if you go back, so 0.74 to 0.77, so 2 decimals if you round off, 0.76 is the correct answer. So you can replace 0.76 in this, okay, which is in the given range. Okay, so one thing that has to be done carefully in such velocity profiles in pipes and all, whenever they give you some radius power, some number here, make sure you make this value as a substitution. Okay, so 1 minus small r by capital R is equal to T is what you make, and then go for the integration. Okay, so normally in case of turbulent flows you will have, I'm just giving you this value, so please keep this in mind. In case of turbulent flows and all, in general for turbulent flows, this n value instead of 1 by 7 it is actually, sorry, instead of 1 by 5 it is actually 1 by 7. Okay, there you will get 1 by 7. Okay, you can write here some hint, if n is equal to 1 by 7, okay, because this is the most commonly used in turbulent flows and all. Sometimes they can give you process is same, everything is same, except this 1 by 5 you have 1 by 7. Okay, so whenever you have 1 by 7, this k value is 49 by 60. Okay, I'm just giving you some value. So if n is equal to 1 by 5, this is 25 by 33, and when n equal to 1 by 7, this is 49 by 60. Okay, so this 1 by 7th law model is generally sometimes used very famously, so that's why I'm just giving you this. Okay, if n equal to 1 by 5, we have just identified 25 by 33. Clear? So but calculation of this mass flow rate is actually important here in this case. Okay, so that has to be taken some care. Normally you take the small elemental area that's available and you go for the integration, multiply it with u and go for the integration, that gives the answer. Okay, so normally these all are based on the mass conservation equation. Basically conservation of mass, you can see I have applied conservation of mass, discharge, and the concept of average velocity is what I have given you. Okay, now let us solve this question. A circular pipe 10 centimeters in diameter has a 2 meters length which is porous. Meaning of that is, this tells you that the pipe has some holes so that fluid actually goes out. In this porous section, the velocity of the exit is known to be constant. Okay, so basically the amount of fluid which is going out through that holes is maintaining a constant velocity. If the velocities at the inlet and the porous section and the outlet of the porous section are 2 meters per second and 1.2 meters per second respectively, average velocity of this emitted discharge, what is going out, okay, is dash meters per second. Look, try to understand this. You have a pipe again, you have some pipeline like this. You have some pipeline like this. Now you see inlet, outlet. Now okay, so this is inlet and outlet. Now what's happening? Basically this pipe has holes all over the 360 degrees. The pipes has holes all over the 360 degrees. Similarly here, means all over the 360 degrees the pipe has some holes, and basically you can observe one thing, the velocity of the fluid which comes out of this, the velocity of the fluid which is coming out of this is uniform. Okay, so here the velocity is uniform. The fluid is coming out of this porous, means basically containing holes. Fluid can actually come out to this. Similarly here, so basically fluid is coming out at some uniform velocity like this. Now tell me one thing. First of all, one thing is very clear, whatever the mass that enters through this face should be equal to mass leaving out through this circumference of this pipe minus mass which is coming out through this, correct? Means if you see, this is m dot in, this is m dot exit, this is m dot out for example, then you know whatever from conservation of mass, you can understand from conservation of mass, what you have, m dot in should be equal to m dot exit plus m dot out, and this is an incompressible flow. We have seen it's an obviously it's carrying some water. I think they have given you, correct? A circular pipe in this porous section, the velocity of the exit is known to be constant. If the velocity is at the inlet, average velocity of the emitted discharge. Okay, it's fine. So let us suppose there is some fluid like water, for example. So if you take density into discharge that is coming in, density into discharge that is emitted out, plus density into discharge that is coming out. Okay, so density gets cancelled. So Q in is equal to QE plus QO. Now you know this can be written as velocity at the inlet into area at the inlet is equal to velocity of the exit into area available for the exit plus velocity at the outlet into area available at the outlet. Now one thing is very clear. If this diameter of the pipe is D, A inlet and A outlet, they are same, correct? Whatever is the flow area available here, same is the flow area available here, which is pi by 4 D square, correct? This is a pipe. Now I want you to tell this A exit means whatever is the A emitted, basically A emitted. Okay, so A emitted. What is the area available for the fluid which is emitting out if this length is actually L? The length of the flow, the length of the pipe is actually L. Okay, so the length of the pipe is L and the diameter is D. So please tell me for the fluid, look, let us suppose if this is the pipeline, for example. Okay, so let us suppose if this is the pipeline, then fluid is coming out radially in all the directions along the length of the pipe. Then please tell me what could be the area available for the exit. If this is a pipe of diameter D and length L, then tell me what could be the area available for the fluid exit, which is exiting like this radially in outward direction throughout the length of the pipe. So please type in the chat box what is the area that's available for the fluid which is coming out through radially in all the directions. It's a porous, means it has small holes almost. So if you see the complete area which is available, so please tell me. Assuming there are large number of holes, okay, very high number of holes are there. So please tell me, like a kind of shower, for example, if you see. So can I write this value as pi into diameter into L? Can I write this, which is nothing but the surface area of the disc, the surface area of the pipe actually? Can I write this? Yes or no? Can I write this? Pi into D into L is nothing but the surface area. Pi dl minus pi by 4 d square. Pi by 4 d square is actually this area, right? Pi by 4 d square is actually the area available at the inlet and outlet. Look, whenever you have a pipe like this, okay, so let us suppose when you have some pipe like this, fluid is coming from each and every point like this in this direction. Okay, it's a porous. So basically fluid is coming out at every point all over the circumference. Okay, similarly here if you see, fluid is coming like this all over the 360 degrees. Then can I say the area available for the flow is basically pi d, means basically if you see at any section fluid is coming out all the 360 degrees and the pipe is of length L. So total area about which the fluid is coming out is nothing but the surface area of the pipe, correct? What is the surface area of the cylinder? Pi d into L, correct? So that's how we have pi d into L is the area available for the fluid to come out, correct? Okay, Shrikant, did you get this? Normally if you see, pipe has this pi d perimeter which is circumference, and this is over a length L. So fluid is actually coming out at each and every point. So we can write pi dl. So now if you substitute here, this implies velocity at the inlet into area at the inlet, which is pi by 4 d square, is equal to velocity at the emittance plus area of emittance is how much? Pi dl plus outlet into pi by 4 d square is what you have here. Okay, so if you simplify some terms, then let us see, d square, this d and this d gets cancelled, pi in every term gets cancelled. So if you see, if you want VE, this implies emittance velocity is equal to inlet minus outlet V inlet minus V outlet by 4 into V inlet minus V outlet by 4 into D by L into D by L. So this is the expression for V emittance. So what, let us substitute the expressions. What is the inlet value? We can see at inlet the fluid is coming in at 2 meters per second and leaving out at 1.2 meters per second. Okay, then what is length? 2 meters length, and diameter is 10 centimeters. That's it, all the 4 values we got. So 2 minus 1.2 by 4, 2 minus 1.2 by 4 into diameter, which is 10 centimeters. If we convert to meters, 0.1 by 2 meters length, correct? The pipe is of length 2 meters. You can see that's clearly given. So if you simplify this, let us see, this is 0.8, so this is 0.2, so 0.1, so 0.1 into 0.1, 0.01, 0.01 meters per second is the correct answer in this case. So this is the correct answer. Okay, so V is equal to 0.01 meters per second, because you see, simple calculation we can do 0.01 meters per second. So 0.01 is within this range. Okay, so 0.01 is in between them. So 0.01 meters per second. Okay, so that's the correct answer. Simple question. But the only thing here, the crux is identifying what is the area available for the this emitting out. Okay, so this is nothing but the area available at emitting out is nothing but this complete surface area of the cylinder, which is nothing but the pipe, surface area of the pipe. Clear? So that's how we can solve this. Okay, so I hope you have understood this question, why I have written this pi dl here. Clear to both of you? So please type in the chat box, is this clear to you? Did you all understand how we got this A emitted is equal to pi dl? Okay, now let's go for the next question. Simple question. For a 3-dimensional flow field described by V bar is equal to, this is vector, okay, V bar is equal to y square plus z square I, which is which is bold, which means vector, plus x square plus z square j plus x square plus y square k. The components of rotation is omega x, omega y and omega z are given. So velocity profile, if you see, y square plus z square I plus x square plus z square j plus x square plus y square k. Okay, so these are the components. So you want angular velocity components. Okay, so see here carefully, let us see, omega bar is equal to half times of curl V. So let us write half times of I j k dou by dou x, dou by dou y and dou by dou z, y square plus z square, x square plus z square and x square plus y square is what you have. Okay, so this is equal to half times of I bar times dou by dou y of this quantity, which is 2y, minus dou by dou z of this quantity, which is 2z, minus j bar times of dou by dou x of this quantity, 2x, minus dou by dou z of this quantity, which is 2y, plus k bar times of dou by dou x of this, which is 2x, minus dou by dou y of this, which is 2y. So this is the vector. Now just one thing, please be cautious here. Look, whenever you are writing omega bar, your intention is omega xi plus omega yj plus omega z k bar, correct? This is the vector what you mean. But when you are writing this expression, there is a minus sign here. Okay, so that minus you have to make plus, because here there is plus sign, here there is plus sign, and for y component also there should be plus sign. Okay, so if you want to convert this to plus sign, then a minus goes here as multiplication. Okay, so this conversion is very important, otherwise you will lose marks. Okay, because when you are writing angular velocity vector, your intention is to put a plus sign here. If you don't make this plus sign, you will get omega y as negative value. You should be a little careful, because in determinants we put plus and minus alternatively, but that don't happen in this vector. Okay, so now if you see, this 2 can cancel 2 that is present in every term, So if you see, the angular velocity vector is y minus z I bar plus y minus x j bar plus x minus y k bar. So what are the components of the acceleration? Omega x is equal to y minus z, omega y is equal to y minus x, and omega z is equal to x minus y. Okay, now they might have given you some point. So what is the point? Okay, point is not given, fine, but actually point should be given, na? So E is described by v bar is equal to this, the components of rotation. Okay, let us keep one point at let us see what are the values. 1 2 3 let us take. Okay, because looking at those values it could be something like that at 1 2 3, because you see these are, so the differences cannot exceed 4 2 or something. So let us see. So this implies at 1 comma 2 comma 3 a point has to be given, otherwise you cannot do this. So this implies omega x component is equal to y minus z 2 minus 3 minus 1 radians per second, omega y is equal to y minus x, so 2 minus 1 radian per second, omega z x minus y minus 1, x minus y is minus 1 radians per second is what you have. Okay, so 1 minus 1 1 minus 1, so minus 1 1 minus 1. Okay, I think here there is 2, maybe some different point is what they mean, but normally when you take 1 2 3 these are the components. Okay, so if you take 1 1 1 then all these things are zeros. Okay, so there might be some different point where they have asked, we have missed the point, actually point is not given, but point should be there. I think we missed this. So omega x is equal to minus 1, omega y equal to 2, omega z equal to minus 1 is what you got basically here. So means y minus z is equal to 1, x minus y is minus 1, like that. Okay, so basically this at this point, if you want to calculate at this point, these are the components. Okay, whatever the points they give you, just substitute in place of x y z, you will get the components. Okay, I think here the vector got missed, the point got missed actually, so that should be there. Clear? Okay, fine. So let's go quickly. I think we have 2 more questions to solve. Okay, one more question. A flow is described by the stream function psi is equal to, okay, psi is equal to 2 3 times of xy. Okay, the point at which the velocity vector makes a magnitude of 4 units and makes an angle of 150 degrees with x axis. Okay, so you want on this stream function the point at which the velocity vector makes 150 degrees actually. Okay, so the velocity vector makes 150 degrees with x axis. This should make 150 degrees with x axis. Okay, 150 degrees with x axis, and magnitude of this velocity vector has to be 4. Let us see what are the points. So if you see this, we know u is equal to dou phi by dou x, which is nothing but dou psi by dou y, and v is equal to minus dou psi by dou x. Now if you differentiate this partially with respect to y, you have 2 root 3 x, and v is equal to minus 2 root 3 y. So obviously look, this is 150 degrees, correct? So if you resolve this, you have y component and x component. So if you see, y component is positive, x component should be negative. Okay, so now if you see this, tan theta, because this is velocity, so tan 150 is equal to minus 2 3 y by 2 3 times of x actually here. Okay, so now if you here, if you see, tan 150 is nothing but minus 1 by root 3, so minus 1 by root 3 is equal to 2 root 3 gets cancelled, so minus y by x actually here. Okay, means one thing is very clear, x is equal to square root 3 times of y. X is equal to square root 3 times of y actually. Okay, means if y is equal to 1, then x should be square root of 3. Okay, so definitely this is not the answer, and this is also not the answer. Okay, so one of these two is actually the correct answer. Okay, so let us see here, if x is equal to square root 3 times of y, means x should be actually larger than y, correct? So but in both the options, I think again there is some typing mistake here, but anyhow let us calculate the components. I think 1 comma root 3 could be the correct answer, because if this is 2, this is also not the correct answer. Yeah, C is the correct answer, but with I think coordinate should be interchanged. Okay, 1 comma 0.577 I think. Okay, so anyhow, let us see. Magnitude of velocity should be 4. Magnitude of velocity should be 4 units, correct? So this is x component of velocity and that's y component of velocity. So this implies 2√3x whole square plus 2√3y whole square is equal to square of this, which is 16, correct? Because you see this square is equal to 16. Magnitude of velocity square is 16. So if you simplify this, 4 3s are 12. So 12 times of x square plus y square is equal to 16. So 4 table, cancel this 4 times. Okay, now what is this x value? Square root of 3 times y. So if you replace here, 3y square plus y square is equal to 4. So this gives you, okay, so y 3 times of 4y square is equal to 4. So if you simplify, y is equal to 1 by root 3. If y equal to 1 by root 3, then obviously x is equal to 1. Okay, so the point at which this coordinate comes out is x comma y is equal to 1 comma 1 by square root of 3. And what is square root of 3? Obviously 0.577. You know this. Okay, so 1 by square root of 3 gives you 0.5773. 0.5773 is what you have here. Okay, so that's basically the so this point which is with inverted coordinates. Okay, so if you see, this is 1.00 and this is 0.5774 whatever. Okay, so this is the correct answer. C is the correct answer. Okay, because you know clearly here you have identified x is equal to square root of 3 times y is what the correct angle is. Okay, so tan 150 is tan 180 minus 30, which is minus 1 by root 3 is equal to minus 1 y by x. From there you identify this equation. Clear? So I think some coordinates got interchanged maybe somehow, but C is the correct answer when coordinates are interchanged. This is 1 and this is 0.5774. Okay, so this point somewhere here, if you see, this point is 1 comma 0.5774. Okay, clear? So let's go for the next question. Let us see, at a radial location r1 in a horizontal plane, the velocity of a free vertex becomes the same as that of a forced vertex if the pressure difference between r1 and r2, r2 being another radial location in the same horizontal plane with r2 greater than r1, the pressure difference between r1 and r2 in the forced vertex becomes twice that in the free vertex. Determine r2 in terms of r1. So see carefully here. It's given at a radial location r1 in a horizontal plane, the velocity of a free vertex becomes the same as that of a forced vertex. So let us see. If you have, for example, 2 radii. Okay, now let us suppose if this is the point, this is some center, so that this distance is r1 and obviously this distance is r2, for example. Okay, now if this point r1, it's given at a point r1, means basically at this point velocity of free vertex is same as velocity of the forced vertex. Means if you see, if you take free vertex and if you take forced vertex, for example, v theta at this place is c by r1 and here v theta is r1 times omega. Okay, so this is what you have. Now given these two are equal basically at the same radial location r1, so this implies c by r1 is equal to r1 times omega. So c by omega is equal to r1 square maybe. Okay, so something like this. Now what is the pressure difference between free vertex and forced vertex actually between the points? Okay, so let us suppose if you take this as first point and this as your second point, then we know in case of free vertex, P2 minus P1 in case of free vertex is equal to rho c square by 2 times of 1 by r1 square minus 1 by r2 square. Correct? This is what you have. Now what about the case here? P2 minus P1 in case of forced vertex is equal to, so what is the pressure difference in this case? Rho omega square by 2 times of r2 square minus r1 square. So this is what you have here. So it's clearly given that the pressure difference, if the pressure difference between r1 and r2 in forced vertex becomes twice that in the free vertex, means this P2 minus P1 of forced is equal to twice that of P2 minus P1 in terms of free vertex. Okay, now let us substitute and let us identify certain things. So this implies P2 minus P1 of first is equal to rho omega square by 2 times of R2 square minus R1 square. 2 times of this free case is rho C square by 2 into 1 by R1 square minus 1 by R2 square. So if you take LCM, we have R2 square minus R1 square divided by R1 square times R2 square. Okay, so this is what you have. But from this equation, C is equal to omega R1 square, correct? So C square can be replaced with this, C square can be replaced with something like rho times C square can be written with omega square R1 power 4. Okay, so because this is C1 square. Now let us cancel out some terms to identify the relation. So density and density, omega square and also omega square, R2 minus R1 square and R2 square minus R1 square. Okay, so 2 and 2 gets cancelled. So now if you equate these two things, we know this R1 square can cancel this R1 square times again. So basically R1 by R2 whole square is equal to 1 by 2. So this implies R2 is equal to square root of 2 times of R1 from this relation. Okay, so that's how we have this. R2 is equal to square root of 2 times R1. So whenever the second radial location is square root of 2 times of the first radial location, then this pressure difference will be twice, provided this velocities are equal actually. Okay, so R2 is equal to square root of 2 times of R1 actually. Okay, so this is the correct answer in this case. Clear? Because we have just seen in today's class itself the pressure difference between 2 points in a forced. Why I didn't consider the z's? Because it's clearly given the vertex is in the horizontal plane, means it's in the horizontal plane, so that there is no difference in z between any 2 points within the vertex. Clear? Okay, fine. So please type in the chat box, is this clear to you? So please type it in the chat box, is this clear? Okay, so let's go for the next question. So please solve this question, then we will go for the control volume analysis. So solve this question. This is the last question I think I have. I kept some 13 good questions actually. Yeah, okay, fine. So this is the last question. So please solve this and tell me the answer. Solve this question. Solve this question and tell me the answer. A closed cylinder 0.4 meters in diameter and 0.4 meters in height is filled with oil of specific gravity 0.80. If the cylinder is rotated about its vertical axis at a speed of 200 rpm, the thrust of oil, basically force exerted by the oil on the bottom cover of the cylinder, is dash newtons, correct up to 2 decimal places. Okay, so we have seen in today's session, you have rotated a cylinder. So when you rotate a cylinder, we have seen directly the expression. If you want to use, you can use pi rho r square omega square by 2g, something we have done, omega square r power 4 by 4 if I'm not wrong, correct? This is the expression, plus weight of the fluid. So what is weight of the fluid? Pi r square h is the volume into density of the oil into g, correct? This is the expression I think, if we are not wrong, this is the expression I think we have evaluated. Okay, because on the top cover I generally remember this pi omega square r power 4 by 4 plus weight of the oil, what we have seen is nothing but pi r square h into rho g, correct? So let us substitute the values. You can take pi rho constants, pi rho times of omega square r power 4 by 4 plus r square h into g. Okay, so we have this expression. So rho into pi r square, or else if you see, if you take r square also out, rho times of pi r square multiplied with omega square r square by 4 plus rho pi r square into h into g, correct? This is what we have, gh, correct? So pi r square if you take out, density also if you take out, we have gh. Okay, so this is the expression. So let us substitute directly. So let us substitute this density. So what is density? It's given oil of specific gravity 8.8. So density is 800 into pi into r square, radius is diameter is 0.4, so radius is 0.2 and height is 0.4, so radius is 0.2, so 0.2 square into 0.2 square by 4 into omega square. So what is omega square? This is given, rotation is 200 rpm, so omega is equal to 2 pi n by 60. So this gets cancelled and this is 3, so 20 pi by 3 radians per second. 20 pi by 3 radians per second. So if you square that, 40 pi square by 9 plus height, which is 0.4 into g, 9.81. Okay, so let us simplify this value and let us see what is the calculation. So this is going to be 10 times of this. Okay, and this basically 0.2 whole square is 2 by 10 whole square, so this is 4 and this 2 zeros can be cancelled actually. Okay, so that's it. I think we can do the maximum calculation. Fine, let us start calculating. Let us calculate this value. 0.04 into 10, 0.4, 0.4 into pi square by 9, 0.4 into pi square by 9. Okay, so this value we got 0.4 into pi square by 9 plus 0.4 into 9.81. Okay, so we got some value 4.367 into 32 into pi, 438.52. Some more calculation. 4 8s are 32, right? 32 into pi. Is this clear to all of you? Pi omega square r power 4 by 4 plus gh, right? Plus g into h. So h is this, g is this, then r square is this omega square. So 10 pi square by 9, correct? So 25 by 3 is, it is 400, right? So it's not 40, 400 actually. One more zero is there. I think we missed there. 400 pi square. Okay, so that's 100 actually. So this is 4 into pi square by 9. Let us perform this calculation again carefully. So 0.04 into 100, 4 into pi square by 9. So 4 into pi square by 9. Okay, so 4 into pi square by 9 plus 0.4 into 9.81. Okay, so if you do this calculation, we got some value into 32 into pi, into 32 into pi. So 835.46, 835.46 newtons is the thrust or the load that actually acts on the bottom part of the cylinder. So 835 point something 46 is the correct answer. 835.46, 2 decimal places, so 46. So 835.4 is within this range. Clear? So that's how this is the correct answer. 832.29 to 838.29, where 835.46 is somewhere in between. Clear? So this is a simple calculation. We have seen weight of the fluid plus thrust acting on the top plate. Okay, so thrust acting on the top plate, I have, since we have just recently derived in previous session, I have got this value. So that value plus weight of the fluid gives you the total bottom thrust that's actually acting on the plate whenever this cylinder is revolved at or rotated at 200 rpm. Clear? Okay, so with this we close this differential analysis of fluid systems. Okay, clear? Now let us start this introduction to this control volume analysis. So basically, what is control volume as per your understanding? In thermodynamics you might have seen this. Okay, we'll do a lot of control volume analysis. So what is control volume as per your understanding? Control volume. What is control volume as per your understanding? Please type something. Okay, whatever you know about it, type something about it. So please type in the chat box. So tell me, what is control volume? Any one of you, anything, whatever you know about control volume, previously heard about it, you might have some data, right? So type it in the chat box. What is control volume? Any idea? Volume having constant mass. Need not be. It can change if it's unsteady. Okay. Or let us suppose you have a tank. Slowly I opened a tap into it. Then what happens? Mass inside it changes, but volume is fixed. Okay. So tank volume is fixed. Slowly you are sending in mass, so mass changes, but volume is fixed. Correct? Now let us see here. Basically, a region in space which is under study. So you have chosen some volume for your interest. Like for example, look, let us see, if you take a plate, for example, let us suppose something is coming. Okay, so let us suppose you have something like this. For example, you have something like a plate like this. Let us suppose if you have this plate like this, for example, let me take plate with different color. So let us suppose you have plate. So let us suppose there is some fluid which is coming like this. Okay, so let us suppose there is some fluid which is coming like this and getting diverted because of this, for example. Then if you want to study, for example, the force acted by the fluid, the force being acted by the fluid on the plate, or the force the fluid is exerting basically on the plate, then you know definitely the force, you know Newton's third law. Basically, if you try to understand carefully, what is Newton's third law? Look, every action has an equal and opposite reaction, correct? Look, basically if you see, if first of all, before telling this, I want to ask you something, some general funda. Look, normally this is the volume which you are interested in at that point. So see here, this is actually a control volume in this case. Plate, fluid jet, control volume. Now, see the thing, I'll ask you one question, try to answer this. What is Newton's third law of motion, which many of you might know since your childhood, you might have used it many times actually. So what is Newton's third law of motion in mechanics? Of course, I'm asking, we are talking about fluid mechanics. So what is Newton's third law of motion? So please tell that. So please tell me, what is Newton's third law of motion? Type it. It's okay, I'll give you some time, but please type it because I'm going to tell you some, important thing out of it. Every action equal and opposite reaction. Every action has equal and opposite reaction. Action equal to reaction. Okay. So normally we know that if you take a ball, for example, and if you throw it onto a wall, okay, then the ball actually comes back, correct? So going of the ball means traveling of the ball is action, and coming back of the ball is actually reaction, correct? Yes or no? So please type in the chat box, have you heard about this? Correct? Yes? Yes, but actually it's no. Okay, look, I'll tell you. I'll ask you one question, try to answer that. Every action has an equal and opposite reaction. Okay, let us suppose if I throw the ball onto a wall, for example, then obviously ball actually comes back to my hand. So traveling of the ball is action and coming back of the ball is reaction. This concept is purely wrong actually. Okay, because I'll ask you one question, you will automatically understand that. Let us suppose if I take my phone, for example, and if I throw it onto the wall, for example, will I get it back? Tell me. Same person, same force I have used. Let us suppose some 10 newtons force I'm using. So in one case I have thrown the ball, in another case I am throwing my phone actually. Okay, then will I get back my phone? No, I won't get. But as per your definition, every action has equal and opposite reaction. So definitely when ball is coming back, my phone should also come back, correct? Elastic collision must be there. Who told you? Newton told you. For elastic collisions, for perfectly elastic bodies, every body has equal and opposite reaction. Did Newton tell these statements? Elastic collisions, all these things. Did Newton say this? For elastic collisions only my law is valid. For inelastic collisions it's not valid. Is it? No. Then, okay, I'll ask you one more question actually. Look, when I throw this mobile onto the wall, it breaks, you know this. But let us suppose if I keep this mobile on my palm, for example, and if I keep like this, okay, for example, let us suppose if I'm seeing it like this, then when I'm seeing it like this, will it break by its own? Please tell me, will this mobile break by its own after some time? Will this mobile break by its own after some time? So please type in the chat box. No, it won't break, correct? You know. But then when you are throwing onto the wall, why it is breaking? What is the reason? Is Newton's third law of motion is not about traveling of the ball. Going off the ball is action, coming back of the ball is reaction. This is a wrong concept totally. Okay, we don't understand this clearly since in schools, and of course, you know, we find some teachers teaching even today in the same way. But actually, Newton's law of motion tells you that Newton's third law tells you Newton's third law of motion, because this is very important in this chapter, exclusively in this chapter, it's very, very important. So see why I'm telling you this. Newton's third law tells you every action force has an equal and opposite reaction force. Okay, this in your engineering mechanics you might have been taught about this. So every action force has an equal and opposite reaction force. The meaning is, and you see in many of the textbooks these words are not written, they just write every action has an equal and opposite reaction. So people take the traveling of the ball as an action, which is actually wrong. Okay, the meaning of this law is actually, look, let us suppose if there is a wall, for example, okay, there is some wall actually, something like this. Now let us suppose there is also one ball. Okay, now let us suppose the person is here, standing on a floor. So this person has thrown this ball actually. Okay, so this person has thrown this ball. So whenever this person has thrown this ball initially occupies this position, then slowly it occupies this position, you know, like this, and finally it reaches this position. Okay, so it occupies many positions and finally it reaches that. Main idea is Newton's third law is not valid till this point. Newton's third law is valid only at the point when this ball and wall are in physical contact with each other. Understood? Means basically if you see, whenever this ball slowly reaches this location, means when it is in contact with the wall, what happens is ball will actually exert a force F onto the wall actually. Okay, means if you zoom and try to understand what happens here, if this is the wall which you are seeing, and let us suppose if this is the ball, whenever they are in contact with each other, what happens is the ball exerts a force F on the wall. This is F. Now as a reaction, wall also applies the same amount of force but in opposite direction. Okay, it also exerts the same amount of force. On the ball. So F by wall, and this is F by ball actually. Newton's third law is valid only at that particular point of contact. Okay, so during traveling of this motion or coming back of this motion, Newton didn't talk about anything. Okay, Newton talked about the instant when these two are in contact with each other. See, that's the reason why in engineering mechanics course, when you take the body, when you separate the body, only then you will write the free body diagrams, not in the traveling. Okay, when you will write n and mu n formulas, whatever the reactions involved, you will write only when bodies are in contact with each other. Understood? So that's the reaction force which is developed, and that's why you always say action and reaction occurs as pair. Okay, now the reason is, now whenever if I keep this phone like this, why it's not breaking, but when I'm throwing it, why it's breaking is because whenever, look, whenever I throw a ball, this ball will travel and hit the wall. Okay, just at the point of contact, whenever the ball is trying to apply some force on the wall also throws the ball again back with the same force. So that's why you get the ball back to the hand. Now when I keep this phone like this, it won't break, but when I throw this onto the wall, this breaks. Correct? For breaking of this phone, some force is needed. Yes or no? Correct? So please tell me, for breaking of this phone, some force is needed. Correct? Yes? Yes or no? So please type in the chat box. To break this phone, you need some force. Correct? Now when you are throwing it onto the wall, who is supplying that force? The reaction force from the wall is actually supplying the force which is required to break this phone actually. Understood? So that's why, because if, look, for example, if this is wall, if I go and slowly touch the wall, then definitely this phone won't break. Okay, ball and phone are common. You see, the wall and phone are common in both the cases, but in one case I am throwing, in one case I'm just touching the wall and taking it back. In second case, the force exerted by this phone on the wall is very less, and obviously the reaction is also very less. Phone can't break. Okay, but in the first case, when I'm throwing it hardly, this will exert some good enough force on the wall, so wall will also offer some reaction. Okay, so Newton's third law is valid only at this interface when they are in contact. Okay, now if it's ball, it will actually come back. If it's phone, it will break after taking that force. After taking the force, what happens to the body? Newton didn't talk about it. Understood? Newton just talked at the interface what will happen after taking back this force. If it's a ball, it will come back. If it's a phone, it will break and fall down. But the main thing here is this action and reaction concept is valid only at this interface of the objects. Is this clear to you? Did you all understand the Newton's third law clearly? It's not about traveling of the ball and coming back of the ball. This is, basically some wrong way of understanding it, but actually this is what Newton's third law is. Clear? Clear to all of you? Yes or no? So please type in the chat box. Is this clear to you? Understood? Now, why I have told you this is basically, look, in this case, if you want to calculate force on wall, on plate, let us suppose if this is plate, if I'm calling it plate, force on plate by fluid is equal to minus of force acting on fluid by plate, because they are they are in contact with each other. Force acting on plate, force acting on the fluid by the plate. So these two are actually equal because they are in contact with each other. And normally net force acting on any body in general, this net force acting on any body in general is basically equal to force acting on fluid is nothing but rate of change of momentum of the fluid. Correct? Momentum of the fluid. But of course, means basically if you write in vector form, all this if you write in vectors, this is a rate of change of momentum of the fluid. Understood? So here what we do generally is, this velocity is maintained uniform generally, but this mass, this will take this mass out. dm by dt is nothing but the mass flow rate, because you see in case of fluids it is continuous mass flow. So let us suppose if the mass that is entering this control volume is m dot, we write this as minus m dot times v bar actually. Okay, so this is the force exerted on plate by the fluid. Okay, so force on fluid means force acting on any body is equal to the rate of change of momentum of that body. So that's how you can write this. Clear? So this is how we will mass flow it into velocity. So if you want the force acting in the x direction, we consider the momentum change in the x direction. We will see in tomorrow's session, we deal with one very important concept which is called the Reynolds transport theorem. So there we will see how this expression is coming out basically. Okay, we all know that Newton's second law is net force acting on the body is equal to rate of change of momentum. Okay, we will see how that is actually coming. Okay, from the Reynolds transport theorem, we will observe. Normally, Reynolds transport theorem is one very good connection between Newton law of mechanics and the fluid things actually. Okay, fluid mechanics actually means movement of fluids. Okay, control volume things. So this is one very important thing that actually we will discuss in the tomorrow session. Okay, but anyhow, to understand the momentum change of the fluid, we will select some volume. Here the main interest is to tell you that normally the fluid undergoes some change in momentum because the direction of the velocities and all will change. If this is coming with a velocity v, then here this fluid also goes out with some velocity v, like this. Okay, now the main thing is whenever the fluid is changing its momentum, the fluid is changing its momentum. Momentum change means basically velocity change here, maximum. Okay, because mass flow is constant. Okay, now the main important point is the velocity changes of the fluid is taking place within this volume. Correct? Outside this volume there is no velocity change. Fluid is coming with uniform velocity, but the directions of the velocity or whatever happened is changing within this particular volume of the fluid. So that's why that particular volume is of our interest. Okay, so if you study about that volume, you will come to know the study of or the change in velocity of the fluid. So because of which you know the momentum change of the fluid, you will know about different things actually. So to understand this fluid impact on the plate, we will select certain volume so that studying that volume completely will make us to understand different things actually physically. Clear? So that's why we select certain regions in space whenever things are there. Okay, now try to understand carefully one thing. These control volumes can be of different types actually. If you see, if I fix this plate for example, then obviously the plate won't move, then this volume is fixed. Yes or no? So this dotted line what I have taken is control volume, then that control volume is fixed. But sometimes what happens when the jet impacts, the plate will move. Like for example, you take blades of a turbine. What happens whenever the water jet hits the turbine blade will move actually. Okay, so when turbine blade is moving, means basically in this case, simple case, if this plate is moving with velocity, if I didn't fix this plate will move. Then when plate is moving, my control volume will also slowly move. Correct? Yes or no? So please tell me, will my control volume move in that case? Correct? So please type in the chat box. Can you understand that my control volume also moves in this case? Yes or no? Did you understand how control volume is actually moving? Because whenever the plate moves, then definitely the location or the region in which the fluid velocity changes or something happens will also move along with it. Okay, so that's why in control volumes we have fixed control volumes and also movable control volumes. Okay, so what I am telling you is, if this plate is not fixed, then when this fluid comes and hit this plate will move with some velocity. Correct? So whenever this plate is moving, then definitely this jet need to travel some more distance to again impact with the plate. Correct? Look, let us suppose when this jet is coming and hitting this plate starts moving. Whenever this plate starts moving, velocity changes do not happen here. Correct? Because let us suppose if because of this impact the plate moved to this location in some small time dt. Okay, so let us suppose the plate moved to some small distance like this, for example. Actually this is the location of the plate, but because of the impact, let us suppose the plate moved to some distance like this. Now whenever the plate moved some distance like this, the velocity changes of the fluid will take place in some region very close to this. Yes or no? Means in that case the control volume will actually move, because obviously to hit this plate, the jet has to travel some more distance and velocity changes will occur in the second part. So that's how when plate is moving, the control volume also moves. The main intention here is to tell you control volumes can be fixed or generally control volumes can be movable also. Clear? Because the main important thing is you have to study the momentum changes of the fluid. So when momentum change means the velocity changes of the fluid are to be studied. Sometimes whenever the plates and all are fixed, control volume is fixed. If plates and all are not fixed, then plate moves with the impact of the fluid. So the control volume also moves along with the fluid. This is what I am telling you. Clear? Okay. So please type in the chat box. Is this clear to all of you? Fine. Okay. Now let us try to see. Okay. So this is about the control volumes. Just I want to tell you, make you understand what is Newton's third law of motion, because tomorrow I have to use this, and also to make you understand what are different control volumes. And sometimes control volumes can be deformable also. Okay, how they can be deformable? Normally if we don't use the compressible substances and all, but normally you might have known the balloon case. Okay, so in case of balloons, what happens if you blow a balloon and if you keep there for 2-3 days, what happens? The size of the balloon decreases. Okay, so some mass will actually go out and all these things. So basically control volumes can be deformable or sometimes they can be movable, whatever, but normally in our syllabus we have fixed control volumes and also movable control volumes. That's it. We don't deal with generally deformable control volumes. So we have these things. Okay, now I want to talk about one more thing, which is this mass conservation. Okay, so I want to talk about this mass conservation also actually. Okay, so see here what we have to talk about mass conservation. Look, mass conservation equation. Mass conservation equation in basically if you see continuity equation. Okay, why I am talking about it again? I have already given you. Then why I am talking about it again? Because I want to give you in a different way this time. Look what I will give you. Guys, look, do you know the Gauss divergence theorem in vector calculus? So type in chat box, do you remember what is Gauss divergence theorem in vector calculus actually? So have you studied what is Gauss divergence theorem in vector calculus? If you know this, then my job is easy. Otherwise, I have to tell you what is Gauss divergence theorem also sometimes. So please type in the chat box. Have you studied this Gauss divergence theorem? Studied but forgot. Okay, common reply every time. So see here, I'll teach you. No issue. Guys, look, in my class, we analyze surface to volume. Yes, of course, it connects surface integrals to volume integrals. But I'm telling you, in my class, if you don't know about something what I'm talking, you can always ask me. Okay, I'll be much happy to resolve your doubts. Okay, doesn't matter how small it is or doesn't matter how basic it is. Okay, I'll definitely answer it to the best with very calmness. Okay, I never say that you don't know this, you don't know that, all these things. Okay, you can always freely ask me. So see here, what is this Gauss divergence theorem is? Gauss divergence theorem, one of the very famous and useful theorems, especially for electrical and mechanical people. Okay, so now see what is this Gauss divergence theorem. Look, let us suppose if there is some closed surface, for example. Okay, so this is some volume V, and this is actually a closed surface. Closed surface S, for example. Okay, so you have a closed surface. Now let us suppose you take some small area. You take some small area, for example, somewhere here. So you take some small area dA. Now let us suppose if this n cap is the normal vector for this area. Okay, so n cap is the unit normal vector, outward normal vector. Okay, so n cap, if you see, I'm not writing the statement, but I'm just giving you the hint. Okay, in maths I'll clearly explain you. So see here, if this is n cap, this is outward unit normal vector. Okay, so this is outward unit normal vector. Outward unit normal vector. Okay, so this is outward unit normal vector. So now here if you see, let us suppose if some force is actually acting on this. If some force F is acting on this location, F, for example. Okay, so let us suppose there is some force which is acting on this location. Okay, F bar. So the effect of this F bar or the complete volume can be identified as, so normally the effect of this F on n cap can be written by this direction. So cyclic integral over the complete surface F bar dot dA bar, which we write as F bar dot n cap dA. Correct? So this is the total effect of the F on n cap, like how we calculated the mass flow rate basically over the complete area. Of course it's not closed, it's open in that case, but of course, so if you see over the complete area, this V bar dot n cap dA is what we have written. Similarly, let us suppose if there is some force which is exerted on this need not be forced, some vector by random. Let us suppose if that's a small vector on this yes, that's acting. So this value is actually equal to, I'm not proving this right now. Normally for gate level this proof is not required, it needs some transformations and all, but not doing that. So cyclic integral over S f bar dot n cap dA is equal to integral over the control volume, or generally this is the volume V. For example, if you take V, normally these are our control volumes what we take. So integral over the volume V, divergence of f bar into dV. This is what you have. So this is basically integral over volume V, divergence of f, which is del dot f bar dV. This is how we get. Okay, so this is a double integral and this is a triple integral normally. Okay, and let us suppose if you find this as constant, then it's very simple, the constant can be taken out. Integral of volume dV gives you the total volume of the surface. Okay, so you know integral V dV, if you have this, then integration of differentiation gives, you know, eliminates both, and you have the volume V. So this is actually the volume V. Okay, similarly surface integral over S dA, if you have, that gives you the total area. Okay, we'll see that in the multiple integrals concept when we take mathematics, but right now if you see, this is the understanding. Okay, now this is basically the Gauss divergence theorem, cyclic integral over the complete surface. Okay, at every point of the surface, if you sum up this value f bar dot n cap dA, then this is equal to, or the complete volume, the divergence of this f bar dot dV. Okay, we'll see what is the physical meaning of divergence, curl we have seen, of course angular velocity, we will see divergence meaning. Okay, all these things in you know, in this case. Okay, now if you see this continuity equation, look, mass conservation equation. Okay, so normally you have seen for deriving continuity equation we took some time. Okay, we have taken different elements, we have taken small differential element m dot x plus dou by dou x of m dot x dx. We have seen some complicated geometry there. Okay, but now if you see, look, let us suppose this is a control volume, for example. Okay, so this is a control volume that you have taken for your understanding. So this is a control volume, for example, say this is V, control volume, for example. Now when you take a control volume, obviously that control volume has some surface, correct? So this is called control surface. Control surface. Now if you see, let us suppose if there is some mass which is entering this control volume and leaving, for example. Okay, so let us suppose some mass is entering this control volume and leaving, for example, something like this. Okay, I don't mean the same amount of mass is leaving, it can be anything normally. Now if you see, whenever some mass is entering and leaving, if you want to calculate the net mass which is leaving at any section, let us suppose if you take, for example, a small dA area here, if you take a small area dA, let us suppose if this is unit normal vector n cap, if this is unit normal vector n cap, and let us suppose the velocity vector at this point is somewhere here like this. Okay, so let us suppose the velocity vector is actually something like this, for example, at this point. Okay, so let us suppose this is the velocity vector. If you have, if this is the velocity vector, then if I want to calculate the net mass which is leaving the system, the net amount of mass which is leaving the system, which is nothing but out minus inlet, correct? So net mass crossing the control surface, crossing the control surface, crossing the control surface, or basically net mass crossing the control surface is equal to rate of change of mass in the control volume. Can I write this? Rate of change of mass in the control volume. Can I write this? Yes or no? Means let us suppose net rate of mass here, let us say, instead of crossing, means basically entering, let us say net mass entering the control surface is basically equal to the rate of change of mass inside the control volume. What is the meaning of net rate whatever is coming in minus whatever is going out. That gives you the net which is actually coming in, correct? Can I say this? Whatever is coming in minus whatever is leaving out. If you take this difference, that gives you the net mass which is actually coming in. Net is basically the effective mass which is actually coming in, is nothing but inlet minus outlet. Whatever is coming in minus whatever is going out, correct? Yes or no? Correct. Now, if you see that net mass which is coming in, if I want to talk about the inlet, then see here carefully. See here, let us suppose if you take the same dA here, for example, so see here, let us suppose for example you take the small area dA here somewhere, okay, you take some dA here, for example somewhere here, okay, so somewhere here, for example, if you take this dA, now the outward normal vector is always like this. So the outward normal vector is something like this, n cap. Now to this, you know, the velocity vector is basically around this. So the velocity vector is almost along this, okay. So the velocity vector is along this. Velocity vector is something like this, out, going in. Now at some locations, at some points in the flow, maybe on the other side or at some locations in the flow, it can be anywhere. Like for example, fluid can come in, some fluid can go out in this location, some fluid can come back at this location, some fluid can go out, at anything can happen. So the total effect of net mass that's entering this control volume can be taken as integral over the complete surface S, whatever the surface you have taken, control surface S, for example, integral over the complete surface S, this at this location V bar dot rho times of actually density of the fluid, if you take for example, so rho times of V bar dot n cap dA, correct? Can I say this? Can I say this? Yes or no? Because rho into V bar dot n cap dA comes out here, but one thing that I have to put here, n cap is outward and V bar is in this direction. V is actually inside and n cap is actually outside. So these two are, you know, the angle between these two will be more than 90. So there comes a minus sign here. Understood? So please type in the chat box. Can you understand this? The total effective mass flow rate over the complete surface. Look, when I'm writing cyclic integral, at some locations maybe n cap and V bar could be in the same direction. That's okay. Okay. So I have considered the total effect of mass interaction at the control surface using this integral, correct? Yes or no? Can I write this? So please type in the chat box. Can I write this? I am telling you, this is the net mass interaction across the complete all the points in the control surface, okay. So at all the points in the control surface, at some locations maybe n cap and V bar may be in some same direction, in some locations they can be in opposite directions, doesn't matter, okay. I am taking the net effect over the complete surface. So that's why I have kept a cyclic integral. Why I have kept a minus? Because at this location the angle between these two is more than 90. That's the reason why I have kept a minus sign, okay. Now this should be equal to rate of change of mass in the control volume, which is nothing but d by dt of mass of the control volume, density into V. That V can be written as, or you can write this as integral over the control volume, integral over the control volume d by dt of rho into dV. This is what I have written. The meaning of this is actually, look, what is the meaning of this quantity? This is rate of change of small mass, means let us suppose if we take some small mass within the control volume, then if this volume is dV for example, then the rate of change of mass in this control volume is dou by dou t or d by dt of rho dV, correct? If I take some small amount of mass in the control volume, then this is rho into dV, correct? So the rate of change of mass within this small control volume is rho dV d by dt. Now if you want over the total control volume, integrate it over the control volume, okay. So this is what you have. Now these are the two expressions that you got, correct? So this is rate of change of mass inside the control volume. That rate of change of mass inside the control volume I have taken as, by taking small element, what is the mass flow that takes place in the small element. Okay, so that is given by d by dt of rho dv for this small element. Okay, so and at that small element, let us suppose if the density is rho, for example, okay, the mass can undergo some density changes when it passing through the control volume. For example, you take a nozzle, then what happens at the inlet, the fluid has less kinetic energy, at the outlet it has high kinetic energy. So to balance the mass flow rate, what happens generally, density at the outlet will be less actually, okay, compared to the case. So that's how we have these things. So d by dt of rho dv. Now if you see, so this can be written as cyclic integral over the control surface S rho times of v bar dot n cap dA plus integral over the control volume d by dt of rho dv. This complete term is equal to 0. Correct? Because if you bring this term to the right hand side, then this is the equation that you apply. Now taking Gauss divergence theorem, applying Gauss divergence theorem, if you apply Gauss divergence theorem here, so let us see here. So applying Gauss divergence theorem, so if you apply the Gauss divergence theorem, then here if you see, this I can consider as one vector, correct? Because density into v bar, density is some scalar quantity, so scalar into vector is another vector. Okay, so now if you compare this rho v bar n cap dA with this f bar dot n cap dA, this f bar in our case is nothing but rho times of v bar. So if you apply this Gauss divergence theorem, the thing that we have here is equal to, this implies this surface integral, it gets converted to volume integral. So integral over the control volume, divergence of this rho v bar, divergence of rho v bar over the small control volume dv plus integral over the same control volume d by dt of rho dv. So we write do by dt of dv. This is equal to 0 actually. Okay, so this is what you have. Okay, now if you see, since the integration is over the same small element and of course you see the control volume, so we can write this as integral over the control volume do by dt. This do can be written as do by dt, exact can be converted to partial at any time, plus divergence of rho v bar dv is equal to 0. So here if you see, this choice of dv is independent, means this integral becomes 0 not because of this choice, it can be 0 at any time. So definitely this quantity which is inside this is actually 0. This quantity is 0 because dv choice is arbitrary. You can choose any control volume, so any shape of the control volume. So whatever the control volume, small elemental control volume that you take, this dv is not changing. So that's why if you see, this integrand should be 0. Therefore if you see, your equation is something like do by dt plus divergence of rho v bar is actually equal to 0. So this is the equation that you have actually. And this equation is the continuity equation. Continuity equation. So you see, hardly 3-4 steps, 1, 2 and 3, 4, that's it. Okay, so but understanding vectors more effectively is very much important in this case. Clear? So you have to understand the vector mechanics very carefully in identifying this. Clear? Okay, so this is the same continuity equation that we have derived using the Gauss divergence theorem in this case. Clear? Why I have told you this is basically, we know this mass flow rate equations we will use many times. Okay, so we know that net effective mass that's actually flowing into the control volume is minus integral over the control surface S rho v bar dot n cap dA. N cap dA is the small elemental area that you take on the control surface actually. Clear? So if you see, we will shift this slide to before starting of this derivation. Similarly here if you see, okay, we can keep this Newton third law here, no issue, but this is how we get the control volume. Okay, so is this clear to all of you? wait, what we have told is basically net mass entering the control surface is equal to rate of change of mass of the control volume. So rate of change of mass of the control volume can be written like this. Okay, so consider the mass change in the small volume and integrate it. Okay, so this d by dt of ODV is nothing but mass that is changing in the small control volume that you have chosen. Okay, so integral over the control volume d by dt of ODV gives you this. Similarly, I have given you whenever you have some small area, mass flow rate flowing through that section is rho into v bar dot n cap d. I have given you this expression in the differential flow, actually, correct? In the differential analysis of fluid systems, I gave you whenever if you have some small elemental area, mass which is leaving through that day I have told you the projection of one vector onto another vector, we have told these things. So whenever you write these things, this implies this n cap dA and v bar are actually normal to each other, so you will get the mass flow rate. Okay, so that you have integrated all over the surface S. This minus sign is because we have taken this velocity vector, because v bar is actually entering inside. Okay, if you have taken velocity vector leaving outside, then you might not take this. Okay, then minus will come here, because then rate of decrease of mass in the control volume if it's positive. Okay, so now we have taken this. Now using this minus sign, we have written both the terms on the same side of the equation. Then we applied the Gauss divergence theorem, converted this surface integral to volume integral, and then we have changed this. Clear? So that's how we got this continuity equation in some 3 to 4 steps very easily. Understood? Clear? Everything that we have done is what we have seen in differential analysis of fluid systems, but of course we are talking this now in terms of volume of the tank or something, whatever you take. Basically this continuity equation is what we have seen. Correct? Is this clear to all of you? So please type in the chat box. Is this clear to all of you? Okay, so this is the mass conservation equation that we talked about. Clear? Okay, so we will conclude this lecture here for today, because you know this kind of concept should be taught very effectively. So that's why I have planned 7 lectures for control volume analysis. We will go in a detailed way, so that we can do chapters like dimensional analysis and all can be done very easily. Then we will save some time. But this differential analysis and control volume analysis, these are like a bridge to the complete fluid mechanics. Okay, so we have to talk there. So how dO by dt came? Because you see, we have taken, look, from this expression, this dV is actually fixed. Okay, so dV is some constant volume what you are taking. So dV you take out, then we get dO by dt. Okay, dV if you take out, then we'll get dO by dt here. No? Okay, Eva? Clear? So we will do in that way. So today I made you understand what is control volume, what is momentum equation, applying Gauss divergence theorem, these kind of basic things. In tomorrow's session, we will basically talk about this Reynolds transport theorem and its deductions from that. Okay, so from that Reynolds transport theorem, you can write conservation of mass, this equation, you can write conservation of momentum, whatever the equation we have seen as Euler's equation, we will write that. Okay, means basically whatever the equation we have seen today, like somewhere here. Okay, so if you see this equation, whatever is this equation, we will write, we will see how these equations are coming. Also we will see for angular momentum case. Okay, we have, I think you might have talked about angular momentum in engineering mechanics, so that will be slightly helpful here. We will talk about that once again, and then we will go with the flow. Clear? So this is how we move on with the things. Okay, clear? So fine, then if it's clear, then we will conclude the lecture for here today. Okay, this is the continuity equation, and please go through this Gauss divergence theorem once again. It's very simple actually. You can understand whatever we have done. Only till here we have applied the fluid mechanics for writing mass flow rates and all. Here it's completely mathematics. We have shifted the equation to one side and we have applied Gauss divergence theorem. We converted the surface integral to volume integral. So this we got 0. That's it. Okay. So these things are really some important and interesting things we will see. Don't miss tomorrow's session. Okay, because 75% of the questions which comes from control volume analysis will come. Tomorrow's class is the basic and understanding point for all those questions. Okay, so don't miss the session tomorrow. Clear? And tomorrow also there is one extra class at 4:30, because we missed 2 classes on Friday actually because of some sudden internet issues. There is some cyclone in my locality, so because of that cyclone there was little internet issue. So I couldn't take the class on last Friday. So we ended up with something like this. Fine. Okay, then take care. Thank you all. We'll meet tomorrow at 4:30 p.m. and we will take one extra class tomorrow as well. Okay, so we will meet on tomorrow at 4:30 p.m. Okay.